In our previous lessons, we were working with adding and subtracting your polynomial expressions. Today, we're going to focus on multiplying your expressions. So here for our warm-up, we've got two expressions to simplify. 4 times the quantity x minus 7 and 2 times the quantity x squared plus 4x minus 5. Now we know what's on the exterior of the expression should be distributed evenly to the interior of the expression. So 4 times the quantity x minus 7 should result in 4 times x and 4 times negative 7. So we should have 4x minus 28. Similarly, we're going to do the same thing with the 2. 2 times x squared is 2x squared. 2 times 4x, that's 8x. And 2 times negative 5 is negative 10. Now, previously, when we were talking about distribution in our prior units, if we said the arrow method, some of you like drawing the distribution arrows, if that wasn't working for you, you could always make a box where the exterior number is kind of your width and the interior was the length, and then you can distribute through accordingly. Remember, your length times your width gives you your area, length times width gives you the area. Look for common terms that you can combine and simplify, otherwise you'll have your results. So again, here's your visual representation of 4 times x minus 7 and 2 times x squared plus 4x minus 5. Again, length times width, giving you your polynomial results. So again, how do we multiply our polynomials? We distribute each term of the first polynomial to every term of the second polynomial. Remember that when you multiply two terms together, you multiply the coefficients, the numbers in front of your variables, and then you would add the exponents, just like we practiced with our exponential expressions. We combine like terms when we can, and we always write the polynomial in standard form, right? So you find your highest degree, and you start with that, and your leading coefficient, and work your way down to the constant. So for example, here we want to simplify our expression given. Again, we can think about it geometrically, or we can use the arrows for your algebraic method. Geometrically, 2x to the third is your width, and x to the third plus 3x squared minus 2x plus 5 is your length. Again, you could take your width times your length and find each of the individual areas, which is also what you're doing here. So 2x to the third times x to the third, that would be 2x to the sixth. 2x to the third plus times 3x squared, that would be 6x to the fifth. 2x to the third times a negative 2x, that would be negative 4x to the fourth. And then you have 2x to the third times 5, which would be 10x to the third. Again, no like terms to combine. We have it in standard form in descending order from your highest degree to your lowest. Here we have the expression a squared plus 5 times 3a plus 7. Again, geometrically, 1 is your width and 1 is your length. And we would multiply accordingly. So I could take 3a times a squared, which would be 3a to the third. 3a times 5, 15a. 7 times a squared, 7a squared. 7 times 5, 35. And again, we're going to look to see, do we have any like terms that we can combine? If so, we will. Otherwise, we'll just write it in standard form. No like terms, so standard form would be 3a to the third plus 7a squared plus 15a plus 35. Here we have the expression of 2p minus 3 squared. Again, that exponent of 2 means you have 2 of what's on the inside. So we can think about the algebraic expression like this, or we could also think about it graphically. Again, distributing every term from the first polynomial to the second. 2p times 2p, that's 4p squared. 2p times negative 3, that's negative 6p. Negative 3 times 2p, that's negative 6p. Negative 3 times negative 3, that's 9. We look to see, do we have any like terms? And we do. We've got these that we can combine together. So what would our polynomial be in standard form? 4p squared minus 12p plus 9. Here's another expression, xy squared plus 7 times 3x plus 2y. Again, we could think about it graphically. And then talk about your distribution. So you have 3x times xy squared, 3x times 7, 2y times xy squared, 2y times 7. Well, what results? We've got 3x squared y squared are 21x, 2xy to the third, and 14y. And again, you scan to look to see, do you have any like terms that you can combine? If so, do that. And then you're going to write it in standard form. No like terms, but if we go standard form for your highest degree, typically looking at that x value, you would have 3x squared y squared plus 2xy to the third plus 21x plus 14y. Here we have our expression 3b plus 6 times b squared plus 4b plus 1. Again, if you need the graphical representation, you could do that. And then look at your distribution. So again, all of your lengths times your widths and filling in what you know. Then we look to see, do we have any like terms that we can combine? Well, we see we've got some b squares. We also have some b's. And that will help us also write it in our standard form. So we would have 3b to the third plus 18b to the second plus 27b plus 6. Here we want to write a polynomial for the area of the shaded region in standard form. So we have two rectangular regions, and we know the lengths and widths of each. And the shaded region is going to result from the area of the larger rectangle minus the area of the smaller rectangle. So the larger rectangle has dimensions of 5 and 3x squared, and the smaller one has dimensions of x to the fourth and x plus 8. So if I think about those items and I multiply them together, here I would have 15x squared, and here it would result in the polynomial of x squared plus 8x plus 4x plus 32. And we do have some like terms to condense again, which would be 12x. Now again, the area of the larger one, we're taking away the area of the smaller one. When you are subtracting, remember you're taking the opposite of everything that's on the interior. So this x squared is no longer positive, it's negative. 12x is negative. 32 is negative. All right, and then we look to see, do we have any like terms we can combine? 15x squared minus x squared, that would be 14x squared. And those are all the like terms that we can combine. So the polynomial representation for the shaded region would be 14x squared minus 12x minus 32 units squared. Here we want to simplify this expression. So let's give you a moment to try your method and see how it's going. Now again, some of you like drawing arrows to show your distribution. Some of you like using the boxes to think about the distribution. Both will accomplish the same goals. So as you distribute your polynomials, we end up with the following. And then we're going to look for like terms that we can combine. So we can see we've got some x to the fourth terms that we can combine. We also can see that in our table here. We can see that we've got some x to the third terms that we can combine. And again, you can see that in your table here. And we can see that we've got some x's that we can combine. And we can see that here. And so we just want to write it in standard form and combining those like terms. So our representation would be 12x to the 6th plus 7x to the 4th plus 45x to the 3rd minus 10x squared plus 39x plus 27. So today we're working on multiplying your polynomial expressions. We reviewed how you could use a kind of graphical box representation to help you think about in terms of areas, finding the lengths and widths, right? Labeling those and finding the individual areas and adding up your like terms. We also showed you the distribution arrow methods. Sometimes in the past, your teachers may refer to that as foiling, the first and on the outside, and they go the inside last. You can use arrows to represent that. It's up to you how you're thinking through distributing every term from the first polynomial evenly to the second polynomial, combining the like terms, and of course, writing it in standard form. So highest degree all the way down to the constant.